Howdy, everyone. Happy Wednesday. I hope you're all doing well and enjoying the sunny weather. Uh, the slide I'm showing shows Albert Einstein just about to solve his famous equation. And we know the old adage, if you fail, try again until you succeed. Uh, in case you don't know, let me tell you a few things about Einstein. Uh, we've already discussed the fact that he got the Nobel Prize in 1921 for explaining the photoelectric effect. Most people think he got it for the discovery of the theories of relativity that he had done. Uh, Einstein was born in 1879 in Ulm, Germany. That's spelled ULM. Uh, Ulm has a university, and for many years I had a collaboration with a faculty member there. And in fact, something like 35 years ago, I spent a summer there doing research. Uh, what's interesting is, as I said, Ulm was the birthplace of Einstein. Ulm has the tallest church steeple in the world, I think, unless someone has more recently beaten that. And next to this church steeple is a shopping area, and they used to have cars and things drive through there and everything. Along the street was actually the house that Einstein was born in, and it, for many years, was kept as a tourist attraction. But later, then, they turned the street into what they call a Fußgängerzone, which means sort of a foot-going zone. And so, in other words, a pedestrian area where people could shop. Anyway, so I went to see where Einstein was born, and basically they've had to tear down his house. And they have just a circular memorabilia thing in the pavement. Kind of looks like a manhole cover and says birthplace of Albert Einstein. Einstein left Germany in 1935, presumably because he was Jewish and he didn't like to be around when Hitler was doing his shenanigans. And so Einstein stayed in Princeton, New Jersey for about 20 years until he passed away. In Princeton, they do commemorate the home where he lived in. Tourists can go there and see it. So anyway, a great scientist, contributed a lot to things that we know about. Okay, so let's go back to Chem. And let's see if we can find where we were. Okay, so you remember what we did was we took the harmonic oscillator problem. Potential energy is 1/2 kx squared. We plugged it into the Schrodinger equation. I gave you what the solutions were for this. And then we looked at what the energy levels and wave functions looked like. But first we wanted to demonstrate that the solution worked. And so we had to take second derivatives of, here's our psi naught wave function for the lowest energy level. And when you plug this into the Schrodinger equation, you will get the corresponding energy level. So always keep in mind Schrodinger equations, solutions come in pairs. The lowest one we'll generally call E sub naught or E0, and then psi sub naught for the corresponding wave function. Then the next level, which we call the first excited state, we would call energy E sub 1, and would have energy psi sub 1. So we went through the mathematics. I pointed out there's kind of a nasty derivative you have to deal with, but when you work it through, you in fact find what E naught is, and that corresponds to what I gave you up above. Then typically when we solve this kind of problem, we draw a diagram for the energy levels. And I think we ended last time with me pointing out that there's an oddity. We have a 0-point energy, which means anything behaving according to the harmonic oscillator potential cannot have zero energy. So even if you cool it to 0 degrees Kelvin, the lowest energy the system can go to is this E0. That's an energy 1/2 h nu, and that's as low as you can have. So that'll mean when we look at molecular vibrations, all molecules keep on vibrating even at 0 degrees Kelvin. Okay, so we solve for the energy levels and we also solve for the wave functions. We'll talk more specifically about the harmonic oscillator solutions, but here are the first two solutions. So this is what psi0 looks like. If you look at the functional form up here, you'll see it'll have a maximum at x equal to 0. Then you'd have an e to the -0, which is 1. And so the value of psi0 would just be this term in front. When it gets to be either positive or negative away from 0, then the x squared term is positive, but the minus sign puts the whole thing in the denominator, and so the value of the wave function will decrease. So this is essentially what it does. If you go to psi1, the wave function for the first excited energy level, you'll see it has an x term in there. So it'll actually be positive for positive values of x and negative for negative values of x. So it looks like this. Okay, so wave functions by themselves, as we'll see, don't tell you much, but when you do something with them, they tell you a lot. So we're going to find that squaring the wave function will give us a probability distribution, and later on we will use operators to operate on these wave functions, and that will give us the properties of a particular quantum state. Okay, so let's talk a little bit more about the wave functions. We first saw that the energies for a system like this can only be the ones that come out of the quantum mechanical solution to the Schrödinger equation. We get E0, we get E1, we get E2, and so on. All of the energy levels we saw were given by this formula. And then we saw the energy levels were all each separated by the quantity h nu. So how do the wave functions tell us about these systems? So let's look at that. So first thing I want to tell you is the square of the wave function is proportional to the probability of finding that particle at some particular coordinate. Now keep in mind, psi itself is a function. It depends on x. Psi squared itself is also going to be a function. So it will have different values at different values of x. And at whatever x the values are large, you'll have a high probability of the system being there. Wherever it has a low value, it'll be a low probability. So keep in mind in the harmonic oscillator, you have this thing vibrating back and forth. So the x position is constantly going to be changing. But what the quantum mechanics will tell us, what are the most probable x values where you expect the system to be. And we'll look at that result in just a little bit. Now we do run into a complication sometime, and that's because our wave function sometimes is in imaginary space. It will have the square root of -1 in there. We call that I, as I've indicated down here. I is equal to square root of -1. And if you run into cases like this, you really have to go to the mathematics of complex variables. There's a graduate math course for that. We don't need to encounter it because we're just going to make very simple use of a concept of complex variables. So if you're dealing with concept variables, what you have to worry about is that the wave function might have a complex conjugate that is different. So we write that as a psi star. So instead of writing psi squared, in these cases, we will always say that the probability is psi star psi. And the definition of psi star is that it's exactly equal to what the wave function itself is if the wave function contains no imaginary terms. If it doesn't have an I equal to the square root of -1 there, we will simply use psi star equals psi. However, if psi has an I in it, then we replace that by a minus psi. So for example, let's say the wave function has a term e to the plus ix in it. Then psi star would be e to the minus ix. So for now, that's all I want to say about it. That's what we have to deal with. I think we may only run into this sort of case once or twice during the semester, but this is for you to be aware that we sometimes have imaginary wave functions, but we always want to make sure that the probability function is a real function. In case you haven't run into this before, complex variables can be very useful. I think all of you in this class probably took the organic laboratory and you did infrared spectroscopy. You did the spectroscopy on what's called an FTIR spectrometer. FT stands for Fourier transform. And to get the actual solutions for the spectra, you had to worry about real and imaginary parts of the data that you were collecting. So imaginary space is not such a horrendous thing. It can be rather useful. Okay, I also wanted to mention, and I put this into brackets, the description of psi squared is analogous to the Maxwell equation, which described the properties of light. And in the Maxwell equations, if you square the wave amplitude, then you're going to find that it's proportional to light intensity. Okay, so for the harmonic oscillator, this is kind of what it would look like. Here's psi naught. If you square psi naught, then you get a function like this. So the probability maxima are very much in the same place that you have. So you'd be most likely in your lowest harmonic oscillator state to find that the system is going to be close to x equal to 0, the equilibrium position. But let's look at psi 1 now, and this is a totally different situation. So psi 1, you remember, has a negative part and a positive part. So at x0, it crosses 0. The square of 0, of course, is 0. So the wave function squared is going to have what we call a node, or a point of 0 probability in this function. So when the particle, harmonic oscillator, whatever, is in the first excited state, it's most likely to be here somewhat to the left of 0 at minus x, or an equivalent distance somewhat to the right of center at plus x, but it will have 0 probability of being at x equal to 0. So I may have mentioned this before, but this is another dilemma. How can the system get from the left side to the right side if it can't ever cross the middle? Well, keep in mind, I think last time I told you that we also have something called a time-dependent Schrodinger equation. We are looking at time-independent solutions, and this is the probability you would find at any given point in time. If you turn on the time element, then you can get systems going from left to right. Most often what will happen, the molecule or atom or whatever you have will go to a different quantum state where it can go from one side to the other. And then when you take the time away and you freeze the picture, you get back to the same probability. But I think we can't all help but feel this seems pretty strange. You know, how can you have this kind of probability for a system like this? I should mention there have been lots of experiments done on these systems, and all the theory and stuff that I'm telling you, it's all been validated. So it's not just pie in the sky mathematical thinking that we might have. Okay, so we'll come back to the harmonic oscillator later. We'll look at more detailed solutions of the higher energy levels. And later when we start talking about molecular vibrations, we will also come back to the harmonic oscillator. Okay, so I think I've already done this problem. I think I did this just a few pages ago because I wanted you to see a quick solution that you had when we had the potential energy equal to 0. I'm going to do it a little bit differently this time and show you that we can also have alternate solutions. Okay, here's the Schrodinger equation after we put capital B equal to 0. So this is what we have to solve. And I'm simply going to tell you that this can have solutions e to the ikx. So this is the imaginary I that I just mentioned. You can easily quickly see if you take a second derivative of psi, what you will get is an I squared e to the ikx. I squared is just -1, so it's a real term that you get. So we would have basically a -1 here, and we'd get the energy level would be equal to h bar squared over 2m. Well, sorry, I left the k out. So you would have a k squared out of that. So these are the energy levels that come out of your solution when you do that. Now, one of the things that we sometimes need to do in the course, and we'll need to do this again when we look at the wave functions for the hydrogen atom, is when we have imaginary wave functions like this, we can turn them into expansions. And a mathematician named Euler came up with the Euler formula. And have you seen this in chemical engineering? If anybody's seen it, send me a chat and say yes.
Yes, many times.
Okay, you've seen it many times. Okay, now, do you know where it comes from? Anybody know? Okay, I'm not hearing any, well, maybe somebody knows. Let's see what they say. For years, I've taught this course, and I've always said I'm impressed that mathematicians can come up with things like this. A year and a half ago, in my chemistry majors course, turns out I had a 14-year-old student already taking physical chemistry. And after I said this, that I was impressed by the mathematician, he said, I can derive that formula for you. I said, go ahead, bring it to me next time. And he did. It turns out deriving this formula is not so difficult at all if you think about Taylor series. So we can write a cosine function in a Taylor series, we can write a sine function as a Taylor series, and we can write exponentials as a Taylor series. If you write them all out, you'll find out that this is simply equivalent by going through that. Let's see if there's any more wisdom. Yeah, someone else did answer that. It's a series. So maybe some of you were, if you were in AP high school math courses or had a clever math professor, he might have told you, he or she might have told you about this also. Anyway, I was impressed that this 14-year-old who now probably is about 15 and a half or 16 and close to graduating could come up with this. Okay, so this is just another variation of the solution. Here I've taken the second derivatives, plugged it in, and again, we can see that this is a valid solution to the Schrodinger equation because we do not have any coordinate dependence in the statement for capital E. Okay, so turns out, I mean, this is the same result that I gave you some pages back. Now I put this result into a rectangular box because I want to use it on the next page. And I also want you to note that K, when we solve it from this expression here, can be written in terms of what the overall energy is. So we have an expression of K, and we will use this on the next page. Now, just simple reminder about high school trigonometry. Here's our sine function of sine kx. If k is equal to 1, then the wavelength, lambda, is 2 pi radians. But if k is equal to 2, it becomes half of that. If it becomes 10, it's 1/10 of that. So k affects what the actual wavelength is for this kind of system. So notice here, I'm going to say k is equal to 2 pi over lambda. And I'm going to relate it to the K that I have up here, because this also can be written in terms of sine and cosine terms. Okay, so keep those two terms in mind. We'll now go back to just our conservation of energy expression. Energy is kinetic energy plus potential energy. We've set potential energy equal to 0. First class day, I think I reminded you that momentum squared over 2 times the mass is also the kinetic energy. So what we can do is I can take this expression for the energy that I had on the previous page, and I can take the expression that I had for K on the previous page, put it in here, and then put it all together. So this is one expression for E, but up here we also have E is equal to P squared over 2M. We equate these two things, and you see we get P squared is equal to H squared over lambda squared. And of course, that reduces simply to the de Broglie relationship. So I just went through this exercise basically to show you that Schrodinger and de Broglie are compatible. But I want to point out the caveat. This is for the case where you have potential energy 0 and a particle flying around in free space. So most of the time, we're going to find that our wave properties are not free waves like we imply here, but they're going to be what we call wave packets. Incidentally, Schrodinger discovered or came up with his formulas for the his wave equation. I think it was the winter of 1925 and early 1926. Schrodinger was Austrian, but I think he went to a Swiss chalet up in the snowy mountains, figured out a bunch of equations. One of the formulas he had to play with was the de Broglie relationship. So obviously he had to go through this kind of mathematics to show that his equation would also come up with a de Broglie relation. What Schrodinger also had was he had energy solutions for the hydrogen atom. So we'll talk later about how Niels Bohr from Denmark had come up with formulas for all the energy levels for hydrogen atoms. And so Schrodinger had to play around with all of these to see how this whole business would work. And no doubt Schrodinger also was aware of the Maxwell equations, they were differential equations that could explain light properties. Okay, so my parenthetical comment, one can also start with the de Broglie relationship to come up with the Schrodinger equation working backwards, and this is presumably what Schrodinger did. Okay, I'm going to go through one more example, and I'm going to go through this quite fast because it's essentially what we did just before. Here again, I'm putting in a constant capital V. We did that a few pages ago. And all I want to do is show you what the effect of putting capital V is and what it can tell us about understanding the nature of some of these wave properties. Okay, so same problem. Instead of E being equal to this, it's now E minus V winds up equal to that. This winds up equal to this expression after we put in the K constant. And at the end, we find that lambda is now given by this formula. The previous example we just went through with capital V equal to 0, and we came up with the fact that the energy levels were P squared over 2M, and lambda was, again, de Broglie's relationship. What I want to show you now, and it might be hard for you to digest this in class, but think about it when you go home. But basically, if you put in a positive potential energy, then E minus V is going to be decreased in this expression, and that's going to wind up increasing lambda. So notice this is a minus to the 1/2 power, so it's in the kinetic energy. So that means then the kinetic energy is decreased and lambda is increased. So the message I'm trying to tell you is when you have short wavelength, then that means you're going to have higher curvature and higher energy. Remember, wavelength and frequency uh, and also energy are reciprocally related. So whenever I show you wave functions, if you see a lot of squiggles, a lot of curvature, it means we're going to have a lot of high energy. Mathematically, it means in a Schrodinger equation, the second derivatives are large. So if you didn't follow all of that, that's fine. I just put in the math there. Main thing, just get out of it, is when I show you wave functions, you see the lower energy levels are kind of blobs, and they get more and more wiggly and squiggly with higher curvature as we get to higher and higher energy. And I've tried to explain that here by going through this relationship right here. Okay, I'm going to do a new screen share and see if I can show you what I hope you'll find to be interesting. Hopefully I can do it. Okay, can everybody see the picture of this pretty little 15-year-old?
Yes.
Okay, this is Felicia Krauss. Her family and Schrodinger's family were friends. And in fact, Schrodinger was maybe something like 7 years older than Felicia. And he used to babysit for her when she was younger. But when she got to be about 15 years old, as in this picture, Schrodinger fell madly in love with her, and she apparently fell madly in love with him. And they wanted to get married. And I guess in those days, being 15 wasn't all that early to get married. Problem was, Schrodinger had to get permission from Felicia's father. So Schrodinger went to her father, who was minor nobility, he was a baron, and asked Schrodinger, well, what do you do for a living? And Schrodinger said, well, I'm a student. And the baron didn't think that was good enough to have Schrodinger support his daughter. So he says, no, you can't get married. So here's the first version of the story I heard. It's in a book by Walter Moore, who wrote an old book on physical chemistry. First version is Schrodinger then was still desperate to get married. He went to a butcher shop, managed to get himself a job as a butcher, came back to the baron and said, I've now gotten a job. I'm dropping out of school. I'm going to be a butcher. The baron looked at him and said, no, we're a refined family. Being a butcher is not good enough. So Felicia and Erwin Schrodinger never got married. Now, if you think that's sad enough, it turns out that they kept writing to each other after they each married somebody else until they were both in their 70s. And so it must have been true love in the first place. Okay, well, that's the book story that I learned about why Schrodinger did not marry Felicia. The more recent story I heard, which is probably true, was Schrodinger went to the baron, wanted to marry Felicia. And turns out Felicia and the baron, they were staunch Catholics. Schrodinger was an atheist. And so the marriage was declined for religious reasons. Anyway, I think she's rather cute, and Schrodinger obviously thought so too. Okay, so a little bit of digression there. If I remember, I'll try to also tell you about Schrodinger in the Austrian army in World War I at some point. Okay, next case is I've been writing some solutions to the Schrodinger equation. I think the first day I said, let's try sine of kx, and earlier today I said, let's try e to the ikx. And you'll notice I didn't have any constant term in front of either the sine term or the exponential. It turns out whenever you have a solution to the wave equation, you can multiply it by anything else, And here I'm taking the little constant a to multiply by, and you're still going to have a solution to the Schrodinger equation. So here's a Schrodinger equation where I've replaced psi by a times psi. And you can see it's perfectly valid because all the a terms will just simply cancel out. So we're left with a question. We want to understand probabilities. And if we don't know what to multiply psi by, how do we know what the magnitude of psi star is going to be? So in order to get around this dilemma, what we do is we go through a process called normalization. So here's how we normalize the wave function. We basically say that if we take the probability function and we integrate it over all space, so here in our one-dimensional model, we start from x minus infinity, we go to x plus infinity. If we integrate over all possible values and set it equal to 1, it means if we look absolutely everywhere in the whole entire universe, we'll have one chance out of 1 of finding the system. Well, what does that actually mean? So that actually means, let's say we want to know what is the probability of a system being between x at 0 angstroms and 1 angstrom. In that case, we could integrate from 0 to 1, and if the function is already normalized, that fraction would tell us what part of the time it's in that system. So if we get 0.017 for that region, that means 1.7% of the time the system is going to be in that particular region. So this is also leading us up to the understanding that when we talk about quantum mechanical systems, we're never going to know exactly where they are. We're just going to be able to talk about probabilities. So I warned you that you might have thought you knew what an electron was. When we start talking about electrons from now on, we're going to say that they're spread out over a wide range of probabilities. Okay, well, this is just what I explained. This means if we look everywhere, we have one chance out of 1 of finding our particle, 100% probability. So here's what our integration would look like for psi naught squared. Remember that an integral is the area under a curve, so we say the area under the entire curve is equal to 1.000. If we go to psi 1, this is the kind of area that we're going to have. Doesn't matter that it's going to have a point of 0 value in the middle. A little bit later, I'm going to tell you how to then do the calculation in one small region. But first, I want to go through the mathematics and show you how we find a normalization constant. So I've picked probably the nastiest case that we might encounter, and I've taken the harmonic oscillator function. If you look back in your notes, you'll notice, you'll remember I had a capital N in there that had a alpha over pi term in there. Let's see why we had that and where that comes from. So we're going to start with this and see how it works. In the process, I also want to tell you a little bit about even and odd functions and some of the mathematics of the problem. Okay, so our requirement is this. We want psi star psi integrated over all space to be equal to 1. In this particular case, there is no imaginary term in the wave function. So this will just be the wave function squared. So we have to square psi 0. All of you, I'm sure, remember how to square exponential terms. Basically, you just add the exponents. So it's e to the minus 1/2 alpha x squared times e to the minus 1/2 alpha x squared. So that becomes e to the minus alpha x squared here. Okay, so make sure you remember that. Just as a reminder, I've shown you here, e to the a times e to the b is e to the a plus b. So in other words, as an example with tens, 10 cubed times 10 to the 4th is 10 to the 7th. You just add the exponents when you do that. Okay, so this is what we have to integrate, and we're going to need to go to an integral table to get this. I'll remind you at the back of your lecture notes, maybe the second or third page from the back, there will be a bunch of integral solutions, and some of them are definite integrals, and for this we need a definite integral. I have not as yet ever seen a definite integral book that gives you definite integrals from minus infinity to plus infinity, but there are lots of them from 0 to infinity. So what I want to point out to you here is if we're doing the psi 0 function squared, if we're doing this function here for positive x, here we have e to the minus alpha x squared from 0 to infinity. On the left, we go from minus infinity to plus infinity. This is an even function because the exponent is going to be positive in both cases. So whether I'm at x equal to plus 1 or whether I'm at x equal to minus 1, the exponential term will have exactly the same function. So what this means is this area here on the right side is going to be equal to exactly the area on the left side. So what we can write, and I'm going to do this here, first I'm going to pull the n squared out of it in front of the integral down here. So I'll have 1 over n squared is equal to this expression from minus infinity to plus infinity. I can separate it into both parts, but since the two parts are equivalent, I can just take it to be 2 times 0 to be to infinity. And this is something I can find in the integral table. Okay, well, if we go to the integral table, this is what we find. I said I was now less impressed by the Euler equation, if a 14-year-old could do it. But I'm still impressed by how someone figures out that this integral from 0 to infinity comes out to be a statement involving the square root of pi. All right, well, it turns out this is what you find in the integral table. If you know what your a value is, you just substitute it in. In our case, our a squared is equal to alpha, and so a itself is equal to alpha to the minus 1/2. X is still equal to x. So what we find is 1 over n squared is going to be equal to this. You work out the terms, it comes out to be the square root of pi over alpha. That's exactly what I gave you last time when I gave you the harmonic oscillator wave function solution. So now, from now on, hopefully you all understand why we stick sometimes these very nasty terms in front of the problem. So the harmonic oscillator can get into difficult math, but we're saved here by the integral table, and so we can find what the values are. When we work with sine or cosine terms, we'll oftentimes find that it's very much simpler. Okay, any comments or thoughts or concerns about normalization? Again, the key is a solution to the Schrodinger equation times any constant will still be a solution, but what we want is we want the probability integrated over all possible values to come out equal to the integer 1. Okay, second property that we want for our wave functions is orthogonality. And here we don't have to do anything because if we've solved the Schrodinger equation correctly, they're all going to come out to be orthogonal. And once we know that they're orthogonal and we've normalized them, all the functions we can say are orthonormal. That's just a short way in nomenclature of saying they're orthogonal and normalized. A lot of quantum mechanical solutions nowadays are done as approximate solutions by computers. And so the orthogonality condition has to be taken into account of to make sure that whatever the approximate solution is, that it remain orthogonal. So this feature is important. Some books, when they teach quantum mechanics, they first start off and say, here are the first 15 postulates of quantum mechanics. Maybe number 7 says all functions are orthogonal, and they go on from there. But I think it's a little bit easier if I just demonstrate these one by one as I'm going through right here. So what I want to do first is go back to the harmonic oscillator, show 2 functions that I've given you before. I'm going to write them in simpler form, not write out these alpha over pi terms in front. And I'm just going to call them n0 and n1 as the normalization constants. And I want to show that these 2 are orthogonal to one another. So the definition of orthogonality is whenever you take any 2 functions for the solution of the same Schrodinger equation, and you integrate and you multiply them together and you integrate over all space, it has to come out to be 0. Now, sometimes students get confused on this, so write a note here. The psi I and psi j are solutions to the same problem from the Schrodinger equation. So if I take a potential function with v equal to 0, I will get a certain number of wave functions. Those will not be orthogonal to harmonic oscillator functions. They're only solutions for the same case. Also, notice in the harmonic oscillator case, we can have different values of k, the force constant. If you get solutions for 2 different k's, those functions are not orthogonal. They have to be the solutions from one set of solutions for the Schrodinger equation for one specific potential function. All right, so let's go through the math. We'll multiply them together. We can pull out the constants. And this is then the integral that we have to show to be 0. In the above case, when we talked about normalization, I showed you that the overall integral was even. So the integration at negative x values was exactly equal to the integration at positive x values. Here, it's going to be exactly the opposite. So again, I will separate the integral into the negative part and the positive part, minus infinity to 0. X here is going to be always negative, and so this integration will give us a negative area. On the right, we have this exactly the same integrand, except with an opposite sign. So we're going to get exactly the same magnitude of the area, but with a positive sign. So these 2 things will simply cancel out. And so negative area canceling out positive area. So this proves that these 2 functions are orthogonal. And that's as difficult a problem as I might give you an exam to show that 2 functions are orthogonal to one another. For the harmonic oscillator or any other system, any 2 functions are orthogonal. So psi 0 and psi 27 are also orthogonal. Or let me take a better example. Psi 0 and psi 28 are also orthogonal, but you cannot easily demonstrate that they are orthogonal because it's an odd function. You actually have to go through some hairy math to show that these integrals cancel each other out. So it gets a lot more difficult when you really get into the nitty-gritty of it. But this is pretty much all that we need to know about orthogonality. It's something that always is going to exist. We have a comment or a chat. Someone wants me to repeat something, but I'll repeat the basic picture. Any 2 solutions for the wave function from one set of solutions to the Schrodinger equation, they have to be orthogonal. If you want to prove them to be orthogonal, in our case for psi 0 and psi 1, we can do that on the basis of the integration involving an odd function. And that's because the area under the curve when we're at negative x is always going to be negative, But when we integrate the area for positive x, it's always going to be positive. But since these expressions are exactly the same, except for the sign, the magnitudes are going to be the same, and so they will cancel out. So this is basically what the integration looks like, that integrated area at negative x, integrated area at positive x. The other thing I said was mathematics gets a lot more complicated if you don't have an even function like psi0 and an odd function like psi1. If you have two even functions like psi0 and psi28, they will still be orthogonal, but the math gets more complicated. Okay, so let's return to normalization. I've already said this once, but I want to repeat it again. And I think among the problems that you've been assigned out of the book, there's at least one problem to ask you: what is the probability of finding a system in a certain range of coordinate? All right, let's say this is a nasty wave function squared, or technically psi star psi, all the way from very large negative x up to very large positive x. Once we've normalized it, it means the entire area under the curve is equal to 1.000. I've also told you that psi star psi at any point is proportional to finding the system at that point. If you have a single point, then you don't have a range of values and you would just get an integral of 0. But if we want to know what's the probability of something being in a particular range, and so I've tried to replicate my psi squared here in some crude fashion. If we want to know what is the probability of the system being between points A and B, all we have to do is integrate between those 2 points. So let's say this crosshatched area out of this whole curve, integration A to B comes out to be 0.041. Then that means that any one particle we're looking at is going to spend 4.1% of its time between A and B. It also means, in the more typical case, where you have jillions and trillions and billions and quadrillions of particles, 4.1% of those particles are going to be in that range. A very important part of quantum mechanics involves building electronic devices, and one has to know what is the likelihood of an electron getting through an insulator or things like that. So you have to make sure you're down in the 1 in a quadrillion range of something not being there if you can't afford to have an electron. But this is a straightforward way of, after normalization, of calculating the probability. So you might remember my electron or photon in a dilemma last time. It couldn't decide if it was a wave or a particle, but it also couldn't decide where it was. And we're seeing more of that now, that anything we talk about, we're going to talk about probabilities of these things. Okay, just a couple of comments before we quit. In 3 dimensions, you would have to integrate over dx, dy, dz. Or if you go to polar or spherical coordinates, then this is what you integrate over. This is probably something you saw in your calculus course. Here we're assuming that the size are 3-dimensional. Okay. I think this is a reasonable place to stop. I'll tell you what we're going to start with next time. We're going to talk about what's going to look like a very esoteric problem, but it's going to have real solutions which are relevant when we want to understand thermodynamic properties of systems flying around in space with kinetic energy. So we're artificially going to stick a particle into a 1-dimensional box and let it fly around and bounce between these walls. And we're going to find that we're not going to have arbitrary energies that the system can have. If we had the particle in free space, it would follow de Broglie's relationship. We would know what its momentum is, and really the quantum mechanics would disappear quite a lot. But here we're going to introduce the concept of what are called boundary condition, the fact that we're not going to allow this particle to be outside of the box to the at negative x values or at a length of greater than L. Okay, so I'll stop for today and have time for a couple of questions if there are any right now.
Dr. Lana, what's the significance of all the solutions to a wave function being orthogonal to each other?
It's just a mathematical fact, okay?
Okay.
The significance of it is I've written a lot of quantum mechanical programs myself, and it gets even a little bit nastier. We have to talk about properties like Hermitian. You have to make sure you abide by these. If you don't, you can't create valid approximate solutions. But it's really basically out of the mathematics of it. I might mention, if you're still listening, orthogonality is a little bit like lines being perpendicular to each other. You can say, what's the significance of that? Well, the fact is that they just are never going to be parallel, right? Okay, thank you all. I'm going to sign off.
I have a question.
Oh, okay.
What is the best way to prepare for the exams?
Okay, at the end of the section on quantum mechanics, it might actually be after the atomic spectra section, there are a whole lot of practice problems. In fact, I think I've given you every possible example that you might have. And most of the problems in the book are also relevant to what you might see on an exam. So typically on an exam, it might be about 2/3 problems, and then the other 1/3 might be concept questions. I'm quite sure for this class, since the graders will have to deal with 183 exams to grade, I would try to make some of the concept questions easier to grade and give you a lot of true and false questions. So make sure you understand the subtleties of the concepts that we're talking about. Just based on what we talked about today, true and false question could be, are psi1 and psi7 of a harmonic oscillator orthogonal? Okay, so I haven't specifically written that out in the notes. You're going to have open notes, but you have to understand the concept to some extent to be able to answer that question. Does that help? The other answer, of course, is study. I mean, read the book. Everything's going to be based on lectures, but the book will complement and embellish everything more and give you lots better examples and clarity of what we're talking about. Okay. Okay, if there's nothing more, I will sign off.